Hi, welcome back to the course on multi-agent learning. As I explained in the first lecture, I went through a number of exercises or a number of games with the audience, and these were simple games in which you can decide on a binary action to either say yes or no. Yes would be a 1, to issue a 1, and no would be issue a 0. Yes would be to raise your hand, and no would be to abstain. Or no, would be not raising your hand. To abstain is neither of the two. To abstain from voting. So you were, in some way, you were obliged to participate, and not raising your hand would be taken as a no. In traditional parliament, yes or no is traditionally pronounced, I believe in the US, only as a or nay. The A's are 30 and the nays are 60. You will hear that sometimes. Okay, but it's not that important. So the first exercise I did with the audience to play in rounds. Oh yes, I first divided the audience in groups of four players. Here. And for each round there are two possible actions, yes or no, and the reward per round would be the number of persons with identical actions. And then I asked the groups to go through a couple of rounds of this game and see what happens, and analyze. Now, and I would ask you now to do the same, but as a kind of armchair experiment, as a kind of thought experiment, to predict what would happen. Well, normally you would, for example, choose to be safe and go with the majority. But it's not always the case. You could also choose to go with your friends, or you may make prior to executing a round to make appointments, to agree on all raising your hand or not. So it is allowed. Well, you can agree upon the rule that it is allowed to agree on a certain number of rules, or to agree on the actions you take once you execute the next round. Now I execute a group of 4 players to do the same, but then take the reward as the number of persons with opposite actions. So the maximum reward would be 3, because for example, you would choose to raise your hand and the others choose not to. And the minimum reward is 0, because you all choose to execute the same action. And then the question was to execute this game for a couple of rounds and analyze what goes on, and to explain all informally, just to get a taste of what's going on. Now, obviously the dynamics is more complicated than to reach agreement. So in the first scenario, if you want to discoordinate, as in the second scenario, then the dynamics will not stabilize, because you always want to do the other thing. But really, you should do this live. So it is a silly game, so it's hard to ask a few roommates to participate in this silly game, but you should at least do the thought experiment. And then as a last exercise, I would ask you to execute the so-called game of tragedy of the commons. That is, you want to solicit for a reward, and you will receive the reward if no more than 3 or 4 players will raise their arm. You will receive a reward of 1. But if 4 players raise their arm, you will receive no reward. That's the catch. So the dynamics here is that it's tempting to raise your arm because you want a reward, but if all of you raise their arm, no one gets a reward. That's the dynamics here. And again, I invite you to go through your mind, do a theoretical thought experiment, do an armchair experiment, and try to predict what would be the dynamics. And then I did the same games with the whole class, with the whole room, usually about 80 participants. Not to raise hands, but to make it more physically and fun. You could either, if you agree, you would stand, and if you did not agree, you would sit, remain seated, and we'll do the same. And I can already reveal that the tragedy of the commons in a group of 80 players, where you would receive a reward of no more than 10 people stand, did not work out. So everybody is very tempted to fish for a reward and take his chances, but in subsequent rounds too many participants took their chances, and in the end nobody received a reward. It was very fun. And I remember I did this the first time in last year, I believe, or 2018 as well, perhaps. And it was a very fun lecture, I can recall, because it was quite physical. Okay. So I already mentioned that the 2 intros of Peyton Young, of Peyton Young's monograph, Strategic Learning and Its Limits. Yeah, how will you be able to achieve this? I can explain it now, but I think I will put it on the course website, because you need a password, username and a password, and they will mail that to you. So and then, because the book of the monograph of Peyton Young is very hard to obtain on the internet or through the library, so you will need it by other means. And chapter 7 of the Multi-Agent Systems book of Showman Leighton Brown is just open source book, so you can just download it. That's no problem. But I will mail you right after this lecture about the username and password needed to retrieve further study material. So I highly recommend, if not urge you, to read the introduction of the monograph of Hobart Peyton Young. It's very informal and instructive. And browse, not study or read, but browse through chapter 7 of the Multi-Agent Systems book. Chapter 7 is called Learning and Teaching. It's about multi-agent learning of the Showman Leighton Brown. There they explain, both chapters explain, that multi-agent learning is quite a different beast than statistical machine learning. And well, you have first place you have interaction between learning and teaching, and you have to be very clear about the conditions in which learning and teaching takes place, and what you want, and how you measure success of multi-agent learning algorithms. There are different ways of measuring success. And I can already reveal that there's no consensus on the way how multi-stage learning algorithm should be compared, because it's such a self-referential system. Well, it's hard to further explain now, so I will leave it at that. So let's begin with a simple example that multi-agent learning is not only about learning but also about teaching. So for example, suppose we have the following game on normal form. Let's move the cursor out of the way. And this following game is repeated an indefinite number of times, so not infinitely, that's not the right way of putting it. I would say indefinitely, so you will repeat it without knowing how much times you will repeat it before you will be called away from the game. You will be taken away from the game. So in an indefinite number of times. And you have two parties. The row player who can choose between two actions, top or bottom, and the column player who can choose between two actions, left or right. And for example, if the row player chooses stop and the column player chooses left, the row player will receive a reward in that particular round of 1, and the column player will not receive a reward. And if the row player chooses stop and the column player chooses right, then the row player will receive a reward of 3 and the column player will receive a reward of 2, and so on. Now, you see that the action bottom is dominant for the row player, because in either case the payoff for the row player is higher in either case than if you would be playing top action. So 2 dominates 1 and 4 dominates 3, so it's always better to play the bottom action. However, that's not and if the row player chooses the bottom action, which is a rational thing to do, then the column player obviously can choose between left or right and would choose for left, because it will receive a payoff of 1 instead of 0. But unfortunately, so this is the Nash equilibrium and the only Nash equilibrium of the game, but unfortunately that's not the Pareto, one of the Pareto optima. Because this action profile, top right, with payoff profile 3 and 2, dominates the action profile bottom left with payoffs 2 and 1. So that's a problem. So the Pareto optimum, so the Nash equilibrium is not the Pareto, does not belong to the Pareto front. That's the problem of this game if it would be played on with short-term interests. Now there is a solution. Row can teach column by not by playing bottom but by playing top, and hoping that if the row player plays top all the time, the column player, if you would have any sense, would observe this and instead of playing left, play right. And then the two arrive at the Pareto optimum. So this takes quite, well, depends on the algorithm or depends on the intelligence of the participants, but if the row player is intelligent, he would be playing not the dominating action bottom, but plays the sub-dominant action top, and would hope or speculate upon the cooperation of the row player. in its own interest of the role play. The role player would speculate on the cooperation of the column player in the interest of the column player, and it would thereby help the role player, and it would end in the Pareto optimal action profile. So multi-agent learning does not only involve passive learning, so following your opponent, but also influencing your opponent and try to push him in a certain direction, him or her, or it. Now in this game the payoffs were all quite unique and not symmetrical, but sometimes it's not clear who should teach and when. Consider the following coordination game. This is a game of choosing roads. So in the Netherlands and most European countries, we drive on the right side of the road, and it is a good for both parties. In the United Kingdom and other Anglo-Saxon countries, Australia, Indonesia, which is not perhaps India, I don't know, they drive on the left hand side of the road, and that's also good. But if one party drives on the left hand side of the road and the other party drives on the right hand side of the road, there is a problem. Both would have negative rewards. Well, obviously it is an abstraction from the situation I'm describing, but you get the point. So this is a coordination game. And now let's size down the game of choosing roads to two participants, you and an opponent who is approaching you from the other side of the sidewalk. And now you choose sides. What should you do? Should you choose step left or right? Or you undoubtedly have encountered such situations. For example, if you're holding doors, it's after you, no after you, no after you. So who gives way first? And here's the same. So if the point is, if the situation is entirely symmetrical, then it's not clear who should take the initiative and who should follow. Normally, in normal life, you will take clues by, for example, physical composition of your opponent. If you encounter an Hell's Angel on the other side of the sidewalk, then you would step aside. Still, it's not clear which side, by the way. So it's not a very good example. I'm now come to realize. Now, suppose you're both passive followers. So you're both blindly adapt to your opponent. Then you will start. And if you start miscoordinate, so you step left and your opponent steps right, which is a miscoordination, and you both are adaptive followers, you will see of each other the action you take, and you will adapt accordingly. But then you will miscoordinate in the next round as well. You adapt to the behavior of your opponent, but your opponent does the same. So you will endlessly miscoordinate if you're both passive followers. However, if you're both adamant teachers and you start to miscoordinate, so one of you steps left and the other steps right, you threaten to bump into each other, but you are adamant teachers, which means that you stick with your initial strategy. You will remain to miscoordinate because both of you are stubborn and will not adapt your strategy. So Hell's Angel player will probably be a bully player, and you or will probably then be a follower, then the situation will resolve very quickly. But if the situation is entirely symmetrical, so if both players are followers or both players are teachers, then there will be a problem. And in computer science, such problems are often discussed, and they result with tie breaking, so flipping a coin. So you flip a coin, but if you are a fictitious player or either bully, those algorithms do not incorporate tie breaking, and those algorithms would have a problem if they would be involved in self-play. Self-play is an important phenomenon in multi-agent learning, which all learners execute the same algorithm to learn. So if all learners would self-play in fictitious play, this would be no solution. If all learners would self-play with the help of bully, this would not be a good solution. Another anti-coordination game, the game of chicken. You probably know and heard if you have followed Inleiding Adaptieve Systemen or the multi-agent systems course. So there are two actions for both parties, sway or dare. It's about two cars. It's the same scenario as the scenario that discussed in the previous slide. You have two parties, and the challenge is not to dare, because not to sway, not to evade, but to dare, driving right through, not to step aside. And if you do not step aside, you receive a reward of 1, and your opponent loses face and receives a negative reward of 1. If both of you are a bit on the adult side, you obviously would both sway and no harm done. If both of you are crazy, then you decide to dare, but the consequences are accordingly, and the payoff is a high negative reward. Now, if you come to learn that your opponent is, for example, a bully or an aggressive stubborn opponent who have chosen not to sway, and you have learned that, then of course it's best to play safe and adapt. And you are here. Well, here. If you are the role player, you are here. And if you come to learn that your opponent is a coward or plays on the safe side, then it's best to bully your opponent and choose to dare, and then you end up in this equilibrium. By the way, this game has two Nash equilibria: southeast and northwest. No, southwest and northeast. This is the other Nash equilibrium. And it has a third equilibrium, mixed equilibrium, somewhere in the middle, of swaying most of the time and occasionally daring. That's unstable Nash equilibrium, unstable mixed Nash equilibrium. So I believe it is here, for example, swaying 90% of the time and daring 10% of the time. That's the third unstable Nash equilibrium. So if the behavior of your opponent is known, then your best strategy, your best reply remains or depends on the opponent. So a possible solution could be to probe the behavior of your opponent first to find out whether he or she is stubborn or aggressive. Stubborn or on the safe side, or an adapter. And then, if you've found it out, then to execute. But this is more subtle, because if you do that, then you miss an opportunity to influence your opponent. So if you probe your opponent first and play some mixed actions, you might have missed a window in which you could influence your opponent. So it's not that simple. So this is where the theory of multi-agent learning starts, and think about smart algorithms. Opponents may behave in complex ways. You miss windows of opportunity to influence your opponents. Opponents may differ, and so on. So it's quite more complicated than that. Now, the chapter of Showham and Leighton Brown is a very nice chapter, at least at the outset. The first two sections discuss the area of multi-agent learning and how this area is approached. The first way of looking at multi-agent learning is from the descriptive perspective. You have a multi-agent learning process, for example in economy, firms that influence each other's behavior, or, well, other participants in an abstract setting, and you just try to describe what happens. Or in sociology, if you have a group behavior and you try to describe what happens. For example, the formation of a leader, or the emergence of a group structure, or the emergence of a leader. So what you require from a model, that it is, of course, reflects the reality as much as possible and has theoretical interesting principles. For example, that the strategies of the participants converge to a Nash equilibrium, either in the one-shot game or in the repeated game. These are different things. You don't have to understand this now, but if you repeat a game and both parties have a strategy for executing the repeated game, you may have other Nash equilibria than in the one-shot game. For example, in the prisoner dilemma, you have only one Nash equilibria, but if you are going to repeat the prisoner dilemma, then because of repetition effects and history, you might build up a reputation, and then it is possible to have Nash equilibria in which both parties cooperate. Another interesting theoretical principle is when if you cannot achieve convergence to a Nash equilibrium, you can at least try to prove convergence to empirical frequencies. So matching pennies game, for example, does not converge to a Nash equilibrium, but its empirical frequencies do. You do not now have to understand this. We will discuss this in fictitious play and in no regret learning. And if you can't prove that they converge to Nash equilibria, maybe you can prove that the behavior converges to weaker forms of Nash equilibria, for example correlated Nash equilibria. And correlated Nash equilibria are kind of Nash equilibria with a coordinating device. In simple examples, it would be a traffic light, or in multi-agent learning, the coordinating device is the trace of the play, the history of play. So both parties can see what happened and on the basis of that decide what they do. And it will turn out that most multi-agent learning algorithms, like for example no regret learning, do not end up in Nash equilibria, but they do end up in correlated Nash equilibria. And another interesting theoretical possibility is if the empirical frequencies end up in periodic or chaotic dynamics, which is also interesting. Now, another way to look at multi-agent learning is to look at the normative side, to study how agents ideally should learn to maximize their profit, for example. And this is more relevant to AI, because in AI we can design software and design algorithms and implement them in software to maximize profit. So we could tell agents what to do, what is best to do. So prescriptive is categorically prescribing what to do, and normative is describing what is best to do, but allowing agents to deviate. So norms is you should abide by the norms, but it's possible to deviate from the norms. And then to test those algorithms, for example, through self-play. So letting 5 fictitious players play against each other, 5 followers play against each other. By playing different algorithms through tournaments. Well, then the question is how to set up such a tournament and which other algorithms should incorporate in the tournament. This is far from trivial, and several lectures will be devoted to this question, especially because you have to are involved with these questions yourself once you are programming, because you have to set up a ground table and evolve algorithms through evolutionary algorithms, through the for example, through the replicator equation. And well, the multi-agent learning problem is actually unsolvable, because how well a learning algorithm performs very much depends on the learning algorithms against which competes. And an obvious example, for example, if you have 5 algorithms which are stubborn, for example, Bully, yeah, they will not perform well, because all 5 algorithms are stubborn and no profitable result will be reached. So it is quite an unsolvable problem, and this makes the field of multi-agent learning quite interesting. How do we measure the performance of algorithms once they are designed and implemented? Well, there are several criteria, and Schoen and Leighton-Brown mentioned a few of them, and I will follow them. So this is chapter 7, Learning and Teaching, from Schoen and Leighton-Brown, section 7.2, I believe, from the top of my head. You could require from algorithms that they reach, or at least approximate, Pareto optimality in self-play, and they called auto-compatible. Another reasonable criterion is when you require that they at least earn the safety value or the security value. That is, at each point of the matrix, they are able to arrive the maximum in that situation. So if their opponent, it's quite difficult to explain this informally. So if your opponent chooses a strategy, then you are able to make the best out of this strategy. That's the max-min. So a smart opponent would choose that strategy which lets you make the least out of that situation, even if you maximize. And that's the max-min. And safety requirement demands that you are, as a learner, at least able to reach that max-min. So max-min is a formal concept in game theory. So it means if your opponent punish you at the most, you are still making, in that situation, the best out of it. Targeted optimality is another requirement proposed by Peter Stone in 2002. demands that you're at least able to issue a best response against a limited class of opponents. And the feasibility, of course, very much depends on which class of opponents you have in mind. And then, I believe also proposed by Peter Stone and associates is that more subtle forms of performance are formulated. For example, just to give a more subtle example of efficient targeted learning. That is for any level of accuracy epsilon, and for any probability delta, well, 1 minus delta, so both should be chosen small. Not choose be, but can be by an opponent or by a critic be chosen small. So for any accuracy and for any probability, there exists an m, an integer m, who depends not exponentially but polynomially, so in modest terms, on the reciprocals of epsilon and delta, such that after at most m steps, with probability higher than 1 minus delta, those three requirements are achieved within a certain amount of accuracy. So this definition reminds a bit of PAC learning, probably approximately correct learning, that you know that you cannot achieve optimality because most learning algorithms are probabilistic, and so they do not achieve optimality, but you can at least demand that they go into the direction of optimality. So for any precision and for any high probability, you can guarantee for this algorithm that within a reasonable number of steps, those three criteria are satisfied within certain amounts of accuracy and with a certain probability, high probability. So this is just to show that those performance standards can be subtle. Here also is a concession towards optimality, because you know that probably Pareto optimality cannot be achieved, but you can approximate it. Okay. Another requirement is rationality, is that you require from an algorithm that at all times you will give a best response or a best reply, as it's called in game theory, if your opponents settle on stationary strategies. So if your opponents home in on a fixed mixed strategy profile, then you may at least ask from your algorithm that it gives response, a best response to this mixed strategy profile. Finally, but not the least important one, is no regret. That you may demand from your algorithm that at any point you have earned no less than any pure strategy would have. That's also a very important requirement which you may demand from your algorithm, or which you are able to prove from your algorithm. The no regret property. Earn no less than any pure strategy would have. Some learning algorithms I will mention briefly, which you will discuss. Fictitious play we will discuss. That is a prototypical example of a follower algorithm. To follow the behavior of opponents and play at all times the best response at any round. Bully. You try to find out in the payoff matrix of your opponent, which you must know, the best reply, and given this best reply, you can maximize yourself on this best reply. So you will influence your opponent in such a way that he gives a best reply with some action, and you know that this action will give the best payoff to you on this action. So basically you stick to your plan and you hope your opponents are followers. Reinforcement learning, a well-known learning algorithm, is to play action with optimal past payoffs. So you monitor the past payoffs of your actions, are not interested in the behavior of your opponent, the payoff structure of the matrix for your opponent. You're not interested in your opponent at all, but you are only interested in the payoffs of your own actions. So it's quite, what is it? Simple and introspective. No, not introspective, but it's not interested in behavior of opponents, only in own payoffs. Sometimes not play the optimal action, but play the suboptimal action. And you can make this more complicated, but this for another time to discuss. Now, more sophisticated than reinforcement is no regret learning. This that you play actions with optimal hypothetical past payoffs. Because you know you have your own payoff, you hopefully have the entries in your own payoff matrix, so you do know what other actions in that particular round would have paid you off, because you also know, after playing a round, what your opponent did. So if your opponent played left and you played top, after that round you can see, hey, I better have had played bottom, for example. And if you learn along that way, you are learning according to no regret. Bayesian learning is even more subtle and resource intensive. You maintain a probability distribution on a set of possible opponent strategies. For example, if your opponent flips a coin in matching pennies, you will maintain the beta distribution, probably. And that is a set of distributions parameterized by two parameters, alpha and beta, and you update the alpha and beta according to the behavior of your opponent. That's Bayesian learning. So basically, at the outset, you have a uniform distribution because you don't know anything about how your opponent flips a coin. And if you, after a certain number of rounds, you know that your opponent flips a coin, tends to flip a coin 3/4 of the times, and you update your beta distribution accordingly after each round. The problem with Bayesian learning is it is resource intensive, and it may miss out on the actual opponent strategy, because you can only maintain only so much opponent strategies. For example, if you assume that your opponent strategy is reflected by the beta distribution, but your opponent plays another strategy, then it's not. Then you will never learn the true strategy of your opponent. And then evolutionary learning is you have many players, and each player follows one out of n fixed strategies, and they interact 1-1. And some players perform well and others perform less well, and the part of the population that performs well grows. So the idea is that the well-performing strategies grow and the less performing strategies die out. and that's okay because they weren't important. Because they do not perform well, they are not important. So it's okay for them to die out. And we will do that in the programming exercise to compare multi-agent learning algorithms. So what you will implement is fictitious play for sure. Reinforcement learning and variations thereof for sure. No regret learning for sure. Bayesian learning, not, it's too complicated. And evolutionary learning, not as a learning algorithm, but as an evaluation algorithm. It's a kind of tournament algorithm. Okay. It is important to know the context of a learning problem. So it's important to, so different algorithms require different information in order to function. For reinforcement learning doesn't need any information of the opponent in order to function. But other algorithms, for example Bully, require more information, and Bully requires, for example, the payoff matrix of the opponent, which is quite an unreasonable constraint because often you do not know the preferences of your opponent. So different algorithms need different amounts of information. Most algorithms need the structure of the game. Reinforcement learning, for example, does not need that. Some algorithms need to know what their opponents are, how their opponents are playing, or what algorithms the opponents are using. And on the other hand, you must know what the algorithm needs. Well, at the very least, and always, you need to be able to observe your own actions, your own payoffs. There's no exception, any algorithm uses that. Sometimes some algorithms use the opponent's actions. Reinforcement learning does not, but for example following algorithms follow the behavior of their opponents, so need the actions of the opponent. And this is recorded in action profiles of the opponents, so-called counter-action profiles. So action profiles are tuples of actions of your opponents. For example, if you have a prisoner dilemma with 3 opponents, you have a counter-action profile of length 3. And if all your opponents cooperate, then the counter-action profile contains 3 C's. And if all your opponents defect, then your counter-action profile contains 3 D's for defect. And for example, Bully needs opponent's payoff profile. So the fourth observability is rather unreasonable. So the message here is to be aware of the information that an algorithm needs to know in order to function. And some algorithms, like for example satisficing play and reinforcement learning, do not need much information other than its own payoffs and own actions. Now, multi-agent learning is a computer science topic and influenced by economy and sociology, but there is currently no book specifically dedicated to multi-agent learning, unfortunately. As I already explained, there are 2 important monographs on learning in games. The first is a true monograph of Peyton Young, of which we'll discuss a number of chapters on reinforcement learning, no regret learning, fictitious play. And not to forget the introductory chapter This is an important monograph, but quite advanced already and a bit older, which is not a problem. Often too much emphasis is put on whether some source is old or not, but I consider this often not relevant. This is a very important chapter. Read sections 1 and 2 this week of chapter 7. Highly recommended. And browse through the rest of the chapter. Do not read or study it. Just get an impression of what you can buy, what you can have in this course. This is a very charming, the lecture notes of Jorge Vidal. Fundamentals of Multi-Agent System, Chapter 5, Learning a Multi-Agent System is nice. A bit less ambitious, a bit less firm than Schoen's chapter. And then the review article of Peter Thun and Associates. But I won't quote from those. In the next presentation I will discuss Cournot dynamics, which is a small example from economics to show that multi-agent learning can end in quite complex behavior, in fact chaotic behavior. So thanks for watching and hope to see you in the next presentation.